So we finished with this. Let's go on to, okay, so the caching technique we just looked at will work anywhere, right? If you put it in your application, it works in the server just as well. So caching on the server is another very, very important technique, because it might be that the server has to work too hard, do too many database transactions to answer a query, or it might be that it's unavoidable that the server gets asked the same thing over and over again, but because it's a relatively slow operation, the server wants to cache the answer to be able to give it. Because if you think about the fact that we talked about, the cache assumes that people ask, rather that the code is called with a key in a certain pattern, like all the keys are the same for a while or not. The same thing applies to the server, right? It could be that people are asking the server the time of day over and over again, and let's, a made-up example, say that the server would have to call the National Bureau of Standards to find out what time it is over and over again. Well, the server might just cache the time, and that way whoever asks it can answer, it can be answered right away. The servers cache this as well. In fact, it's a very important technique. So for example, what if each time the user wants to see the total price of the items on their wish list? And let's say that for some reason in the user interface evocable, on the bottom of the toolbar, it displays total price of items on your wish list is $700. And the way the evocable app was designed, every time any user first logs in, first looks at the home page of their app, it's going to display that number. Well, the Vocal app doesn't know the price of the items because they might have changed. Amazon changing prices all the time. So the Vocal app turns around and calls the server and says, hey, I'd like to know the total. Well, first, that implementation is Vocal will ask the server, get me all these items so I can get the price, and the app adds them up. They say, the developers say, that's inefficient. Let's just have a single REST call that says, give me the total price of the items in my wish list. And this REST call might look like /user/41 /wish list /total price. They want to write a call that looks like that.
Quick question for you.
Yeah, talk.
Why is this more efficient if the server is doing the calculation? Because if the phone's doing it, then you're splitting up that calculation, and you can do more access to the server in the same amount of time.
Right, I'll explain it. It's not clear, but it may be. Right, so they want to put a URL like this, and they say, that's great, because now we don't have to call the server over and over again, because they might have measured that asking the server for each item individually is a certain amount of network traffic, and then those get brought over to the client, and then of course adding them up on the client is very fast. They may decide that that's a really slow way to go, and in fact it is. I'll explain to you why in a second. So they said, let's implement this, because now the server can go through and get those records one at a time, represent them all on the server side, and then run through the prices and add them up. That's better. However, it turns out that databases are very good at adding things up. So even faster would be if you did a single SQL query, which you could do, to just ask the database to get the total price for those records. That would be one reason. Okay? So here you have an example where the operation appropriately was moved to the server, but that still was slow. And then the next level was, okay, maybe we can have the database compute the total. And the database does that in a highly optimized way. Do you have a question? So okay, that's the second level. But actually you can do more still. If in fact the user interface of Vogable was such that at the bottom of the screen, it always had total in your wish list, and every single user ever who looked at Vogable had to fill in a number here, even if it was 0, then the server might say, geez, I'm getting this request constantly. Well, first level would be maybe the client should be caching this. Right? Maybe the client might say, listen, I'm okay if the total price of the wish list displayed on the window is incorrect for 60 seconds at a time. I'm just going to cache it for 60 seconds and then ask the server. That would be a very logical thing, because now it's not asking the server over and over again. In fact, it's interesting because this would be one optimization, and what I'm going to describe next is another optimization. And it's not clear intuitively which would be the one that we need. Okay? But to play out this particular scenario, you could simply have the server remember that this URL was asked and say, oh, this is the same user again. They're asking for the total price again. It's only been 1 minute. I'm just going to remember the number and return it. So now you've moved the caching to the server.
Wow.
Okay? Very simple. Very simple idea. You have the same problems as before. You have the problem of the cache growing too big. You have the potential problems of the cache growing too big, the potential problem of the cache being out of date. In other words, the price of the items changed. You have the problems of deciding to invalidate the cache if somebody else changes the prices. All those problems that exist on the client exist in the same way in the server. But the impact of this change is greater because in changing the code in one place is going to help everybody. Another little subtle point here is that this optimization on the server could be done without deploying a new app to all the users. So you could actually improve your caching algorithm or put one in where none existed by only making a change on the server. Your apps don't have to know this is going on. They're just asking for the total price for user one, the same as they did before. It's just the answer is coming much quicker. So caching on the server can be done without deploying a new copy of your application, which is huge, which is a huge advantage. Okay, it's a huge advantage not because it's hard to deploy, but because it's hard to get, in other words, and we learned this from Tim either today or tomorrow, it's easy to deploy to the App Store, but what's hard is to get all your users to actually update. And so if your servers are melting down because everybody needs the stupid price in here and you designed this incorrectly, and you're finding that at 1,000 users, your servers are like melting because they're being overused and everybody's complaining, wow, I can fix it on the server in one shot and everybody's performance will improve and nobody has to update the app. Versus, I can improve the algorithm inside the app, I can deploy it to the App Store, and now hope that people actually update the app, which they may or may not do. Okay, so that's another reason why optimizing on the server and caching on the server has a lot of benefit. That make sense? Okay. So a very important thing that was, yes. Do I mention that specifically? Let's see. I thought I had a link to the Memcached. Oh yeah, okay. So another, so here we go. We have another idea, therefore, that says inside the server there is a cache that maps, user 3, total user 3, and that's the key, what the user is, and the value, the value that's returned is the total wish list price, the total price of items on the wish list. That would be a cache, right? So basically it just says in the server there's a table that says for user 4, or it's a memory table, it's $120 for user 5 and so on. This thing can grow just like before, and the code on the server which responds to this particular request checks the cache. If it's there, it returns that answer. But, and since this is a very common thing, it's done very often. But there are, because it's also a very common problem, and the crux of performance problems, or scalability problems on servers very commonly, there's a scheme whereby instead of storing this table either in memory of the server or in a database table, you actually have a special purpose server sitting on the network, who's your caching server. And it has a protocol where people make a request and it gives an answer. Only other servers in your infrastructure can talk to the server. So we'll get a little bit into it. So we have this thing called a firewall. And it's on fire. That's your firewall. Here you have the users, and they have their Android, and they're talking through the firewall to one of your servers. While this queued server is not available to these guys outside. The queued service is providing a service purely to the different computers on your internal network. And it has a very simple protocol. It's a REST protocol. It's got a GET, and it's got a return value. And the GET and the return value, the GET is get value, just like what you do before. Get value, and it's going to return a value, and it has a put T value. It's always, there's a couple more, but conceptually it's all it's got. So this server here is an internal server. It talks a REST protocol just like your app does. That REST protocol is only available to other servers that are behind the firewall. And the REST protocol has only a couple of verbs, get and put. Get me the value stored at this key. Put the value stored at this key. Okay? And in here, using whatever algorithm they choose, is an extraordinarily fast caching server. And so really, as usual, information hiding says that we don't really have to care how this works. All we know is that when now we can look at the code, all we care about using memcache, this is literally out of the doc, is when somebody asks for the total, of the items on user 3's wish list, you can construct that into a key, which might be, instead of saying foo, the key might be total wish list value plus user ID. That's your key. And memcache returns it like that. This is just a call in your code. What happens as a result of this call is one of your different computers in your server talks to the caching server and asks, give me the value. It's very simple. It's exactly the same concept we talked about before, except now, instead of having a local data structure or a local hash map, we ask and get the answers about what's in the cache over the network. And there's all kinds of advantages to this, which I won't go into. But the takeaway here is the idea that memcached is, number one, open source and free, used by everybody, and it's an extraordinarily powerful way to speed up the scalability of your server. So if you get to the point, either in this project or in the future, where you think that you're having scalability problems that will be solved by caching on the server, memcached or things like it are your friend. Okay? Are you guys, I know it's a little bit different from talking about caching as a hash map inside of a method to talking about caching as a service on the internal network. But the principles are exactly the same. If you look at this code, it looks exactly the same before. Fetch foo from, so basically it says, foo is ask the cache, do you know a value for this key? If memcache says I do, it returns it. If not, it asks the data, does a SQL call to get the actual value. This may be the thing that's totaling up the wish list. It tells memcache, here's a new value in the cache for this, and it returns the answer. The pattern here is precisely what I did before with a hash map, except now it's calling these methods, and these methods in turn behind the scenes are calling the caching server. Okay? So that's the idea of putting caching not inside the server, a single server, but actually making it a facility or a service inside your infrastructure. Okay? Okay. Finally, in the area of caching, there's the idea of caching in the cloud. And what that means is simply, there's something called content delivery networks. Anybody ever heard that term? Content delivery networks? Do you want to hazard a definition?